So we have seen that how we can proceed with this multi-level indexing for minimizing the number of searching for a particular record. Now next question will come that what this particular real situation points from the computer science point of view. It actually points from the computer science point of view what we call M-way search tree, or you can say multi-way search tree. Because you see that we have this particular level, and when this level has increased, I have divided this level into many parts, where if you consider this is a particular node contain more than one key value, because these are key values. You can assume in this way. Till now we have seen that a particular node contain only one key value, for example BST, binary search tree. But now we can see that a particular node contain more than one key value, may contain. Not only this, from a particular node we can point to more than two children. So according to this MOS search tree, how we can define it? We can say that each node can have at most m children, at most m number of children. Now second point is that if a node has n children such that n is lesser than equal to m, since it is at most m mean it can be m minus 1, can be m minus 2 also. So I have considered that there is n number of children of a particular node where n is lesser than equal to m, then the node must have n minus 1 number of, I'm sorry, it should not be children, it should be just a minute, I should say that n minus 1 number of, this should be key values. Okay, so then the node must have n minus 1 key values. And third point is that if a node has k number of keys, then the key value must be in increasing order, that is k1 lesser than k2 lesser than kn. So the diagram that you can see over here is an example of 4-way search tree, because this value of m is anything, it depends upon the structure you are making. So in case of a BST, what we have seen, in case of a binary search tree, we have seen a structure something like this: A, then B, and in the side C. So if we just try to realize this particular structure from in this way, so we can say that it is nothing but something like this. This is A, and here we have B, right? And in this side we have C. The similar way that I'm drawing, like what we have seen over here. C, and then this one, and then this one. So what is this? This is what we can say that two-way search tree. So BST is also a special type of M-way search tree where the maximum number of children is 2, and one more criteria is there, that is child is I mean, left child is lesser than its parent and right child is greater than its parent. But it is true for MOS search tree also, because you see, if you closely watch this situation, you see that we have three values over here, and these three values 10, whatever data present over here is lesser than 10. Whatever data present over here is basically greater than 10 and lesser than 20. So if someone try to find out a key value having 16, assume that these are different roll numbers, what it will do? It will check, it will start checking from this point. So we will have a linear search in a particular node. And as we are able to find out the value is not present, we go in the next level. So as a whole, in a MOS search tree, the searching is the combination of linear and a what you can say non-linear search. Because if someone want to find a roll number having 16, it will start checking from here because this is the root node. It is for sure. And it will check it is 10. So it is not 16. And this one is 20. That means due to the third point, the key value is increasing in order. That means if it is 20, that means other data present after 20 is greater than 20. So that means there is no way to having 16 in the right side of 20. That means 16 is definitely present within this 10 and 20 somewhere in this level. And you will be able to find that. So in this way, a MOS search tree has been created, can be created. Now, still there is a lot of flaws. Flaws in the sense that a MOS search tree can be something like this also. You see, as the same amount of data, that if you just put them in an increasing order, you will find 3, 5, 7, 10, 12, 14, 16, 20, then 22, 24, 26, 30, right? And many more, maybe. Because of the space I have not written. But if you do the same thing, you see you will find 3, 5, 7, 3. I'm sorry, I must have a mistake over here. It should not be 3, it should be. Okay, so I should not have this one actually. I have a mistake. This part should not be there. Sorry. I mean, suppose there is nothing. I mean, I should say that this particular there is nothing, means this is null. Okay, so there is nothing, it's null, it's pointing to null. So 3, then 5, 7, now something in the right side, 12 is right, so 7, then 12, 14, 16, 22, 24, 26, then 30. You see, same number of data is there. Now since there is no guideline about the minimum number of key value in this tree, this particular strategy is also correct. This is, you cannot say, you cannot deny that this is not a MOS search tree. It is also a MOS search tree having this particular criteria, because each node can have at most n children. Here also each node can has 4 children. M is 4 over here, right? If the node has n number of children, then it is n minus 1 number of key values, that is also present. It have 2 children, so it has 2 key values. I have not written anything over here, that is later issue, right? So if a node has k number of key values, then it is k1 lesser than k2 lesser than kn, and this is also true over here, that 5 is lesser than 7, 12 is lesser than 14, 16 is lesser than 22, 3 is lesser than 30. So where the problem is? problem is that it is basically increasing the height of the tree. What was actually our not intention? Because due to this nonlinearity, we have seen that if we have n number of data, since we are actually categorizing it in different direction, so total number of searching is minimizing from big of n to big of log n, that we have seen. But if we consider that I have each and every, each and every node contain only one data, so then this is basically again almost going towards big of n, which is not our goal. So what we have done, we have now what we can do, we can put some extra rule over these three cases, over these three condition. We can put some extra rule so that this problem can be minimized, and that will basically convert this normal generalized MOA search tree to a B tree. So it looks something like this. By the way, one more thing we have, that when in case of multi-level indexing, when we find that the index size is becoming too large, we are saying that we will put another level of the index and we will minimize the searching. But question is that who will do this? Is it possible to do manually? It is never possible. That means we have to put some automated method that will basically create a level above the previous level and create a link, something like a tree that we have seen in this particular slide, right? So, and the same time we want to minimize this big of n. So to solve this both problem, this B tree came. So this 3 is actually extra rule that is that's given, that's put over the previous 3 rules to make this B tree, to make the MOA search tree feasible, and as a whole what we call B tree. What are the rules? It is saying that every node other than root node must have at least m by 2 children. So if the at least m by 2, this is as upper value, okay, it is a cell value of m by 2, not floor. So if you find at least n by 2 is not filled up, you cannot go in the next level. So we have restricted to increase the tree in a particular direction. We have restricted that in this way. Now question is that why other than root? It said that it is other than root. Now question is that why other than root? Because if every time that every node have at least m by 2 children, then how the root node will evolve? Because I may have situations that root node will contain only one key value. In that case, it must have maximum 2 children. So obviously it's not possible to say that root node will also contain m by 2 number of children. Whatever the value of m doesn't matter. Second point is that root node can have minimum 2 children, and this is required, yes. When you are creating a root node, you must have at least 2 children. That means what I can say, that in this site, this root node, if I forget about this 4 part, if I consider I have only these 2 parts, So this root node contain these two from here. I have only these two. So not only one, it is not possible. So root node can have contain minimum two children, not below that. And most important point is that all leaf nodes must be in the same level. This is very important, which was not present in the previous scenario. So if we put this extra 3 constraint over this 3 point, we will find what we call B tree. And always remember one thing, when we create a BST, how we create? We create, say for example, we have some arbitrary value over here. Suppose that say 10, 5, 7, 15, 12, something like this. So what we do, we start this one with the root of the tree, then we first do this one 5, then 7, so we left lesser than 10, greater than 5, so in this side, then 15 in the right side, then 12 in this side. So what we have done, we have started from root and we go downward. We are creating the nodes as a leaf node, right? So this is what we call top down approach. We are starting from top, the root is created first, and then we are going downward, adding the nodes in the leaf node. But what happened in case of B tree is that assume that this is my index level 1, and when it will become too large, what I will do, I will divide them into two parts and put an extra level above this who will point this to, that we have seen, right? So basically you see, this is also a tree, and in this tree which node is playing the root node, this is the root node, right, which was not present over here. This root node has been evolved because the size of this particular node in this level has been actually crossed the limit. So some data that was present over here remained present over here, and some data actually go up, came here, playing as a root node. So that means we can see the leaf nodes are in the same level, this third point. And one more thing we have seen, that is this approach of evolving the tree is from leaf to root, this side. So this is what we call bottom up approach. And here it doesn't end. It may happen that root has also been cross the limit, like this, cross the limit. So what will happen in that case? It will become something like, we have this node, this one, some data is present. We have this node, this one present, and here we have seen that this has been crossed the limit. So what will happen? This will be divided again into two parts. But before that, it has to break down. Let's do one thing. Let's take an example to see that how the B tree is created. So let's go for an example. Suppose that let's take some values, arbitrary values, say 10, 7, 2, 3, 5, 8, 19, 16, 15, 20, 30, 26, 25, 23, 28, something like this. Okay, so suppose these are the data. So what will happen in case of BST? What you will do, you will start considering 10 as root, right? So at the very beginning of creation of the binary search tree, you know what you are going to be the root. But in case of B tree, it is totally different, because it is not possible to identify which one is going to be the root until you are going till last, because we are going to create B tree from the leaf node towards root. This root will be involved. But one thing, you have to actually say what is the value of m. What is the value of m? That you have to resolve. So for example, let's take m equal to 5. Yes, no, m equal to 5 is too long. So let's take m equal to 4. Naturally question will come. Okay, let's see. M equal to 4 means a particular node can have at most 4 children. If it is at most 4 children, that means 3 children is maximum possible in a particular node. So that means let's take this 10 first. I mean, let's go for another. Okay, let's take this 10 first. So what I will do, I will put 10 in a node. Fine. Then 7 come. But you see, we have to maintain this particular rule. This k1 lesser than k2 lesser than kn, right? So that means you cannot place 7 after 10. You have to place 7 before 10. Then 2. Similarly, you cannot place 2 anywhere. You have to place 2 over here, so that this is maintained. Then 3 come. So naturally, I mean, as a whole, it has to be written 2, 3, 7, 10. But you know, keeping this 4 in a node is wrong, because of this rule that it can have max at most m children. That means at most m minus 1 key value. So if it is m minus 1 key value considered, that means m is equal to 4, that means at most 3 key value is possible. So this situation is nothing but, you know, as assuming that your indexing becoming too large, and you have to break it down into two ways. So question is that how you can break it? Always remember, we break from m by 2 point of view location. Now when m is odd, then it is easier to do this, because if m is 5, the middle one is third position. But when m is equal to 4, there are two middles. So if you consider, you can take two things. I mean, there is two consideration. I mean, either you can just divide, you can take this 3 as root and go up, or maybe you can take 7 as root and go up. One of these two. So if we consider the left one, the newly formed tree will become what? 2 in one side and 7 and 10 in another side, and 3 will be in the above of the higher level of these two. So you see, 3 is not the first value that was present in the list, but still right now 3 is the root, at least. I don't know what will happen in the, I mean, after inserting other thing, we will see that. And one more important thing, that data is always inserted in the leaf node and then it starts evolving. What I mean to say is that, oh, another situation can be what? Can be something like 2 and 3 in this side and 7 in the right side, only 7, and then I'm sorry, not 7, it should be 10. In the right side and then 7. So this one in this side, you see right side is much more heavy than left one, right? So this is what we call right biased B tree, and this is what we call left biased B tree. Right? Because left bias means because left side is much more heavier than right one, because due to this order value there is no another way. So both are correct. But remember one thing, when you are designing a B tree, either you follow right biased or you follow left biased. Don't take a mixer. Okay. Anyway, so now let's just erase everything and then we start continuing what we were doing. So let's erase this. So assume that we are taking, say, right biased. Okay, right biased. So what will happen if we consider right biased? Naturally, this one will go up, right? So that means next time will happen. It will be something like 2 will be in this side, and 7 and 10 will be in this side. And above this there will be 3. Fine. Now you see 5 will come. Now question is that where 5 will go? 5 is greater than 3, so in this side, and 5 is lesser than 7. So naturally next time what will happen? 3, here I had 2, and in this side we will have 5, 7 and 10. Still you see this is a proper B tree having order 4, because maximum 3 children is there. Fine. Then 8. 8 is again greater than 3. So 8 should come here. Now if 8 come here, then what will happen? 5, 7, then 8 and then 10 will come, right? And naturally this particular situation is violated. I mean the order, right? So situation will become 3. This side we had 2, and this side we have 5, 7, 8, 10, which is not expected. And since we are considering right biased, so naturally now 7 will evolve. And where it will go? It will join to this node. So what will happen? Now new node in that root, it will become 3 and 7. Left side of 3 contain 2. In between 3 and 7 we will have 5. After 7 I will have 8 and 11. I'm sorry, 8 and 10. You see, I hope now you can understand why it is actually bottom up approach. The root is evolved as the data is inserted in the tree. So if you go on continuing inserting 19 and 16, both are greater than this 7, so naturally it will come here, right? So I can take a shortcut just write it over here, that after inserting 19 and 16, it will become 8, 10, then 16, then 19. As simple as that. You can easily understand that. And naturally this particular node will also violate. So what will happen? 8, this 10, the second value will get evolved and join with the root node. So next time what will happen, the scenario, I mean in a I'm doing a step jump. I hope you can understand that. 3, 7 and 10 will join here, and where this 3 in the left side of 3 will have to this side will have 5, this side we have say what, within 7 and 10, since 10 will join within 7 and 10, we will have 8 only, right? And in the right side of 10 we will have 16 and 19, right? And then next come 15 and 20. So you see again 15 and 20, so 15 and 20 both are greater than this 10, so it will join here. And how it will join? It will become basically 15, 16, 19 and 20, right? So 16 should get evolved, right? So if 16 join over here, then what will happen? Let's see. You see, I'm sorry, and let's write here. Let's erase this part because I don't have any space to write. Erase the initial parts. Okay, I'm erasing this part. If you have followed, I hope you can remember, or maybe you can watch my video later again. So a situation will become something like 3, 7, 10 and 16. So 3, 7, 10 and 16 will become on the root. And there will be something in this, but it is not possible. The reason is that order is 4. You cannot have more than 3 children. So that means something from this node, from this current root will get evolved as the actual root. So naturally 7 will get evolved according to the tradition that we are following. So what will happen? 7 will become the root, and under 7 there will be 3, only 3 in the right side, and in the left side, sorry, in the left side there is 3, and in the right side we have 10 and 16. And what we had in the left of 3 will be in the left of 3. What we had in between 3 and 7, 5, it will become the right of 3. What we had in between 7 and 10 will become left of this 10. And in between 10 and 16, 10 and 16, 15, 16, so it will be 15. Right? Because 15 was there. That was inserted. And after, greater than 16 will be what? Will be these two, 19 and 20. That is 19 and 20. So you see that there was no clue that at least up to inserting 27 will become the root. There was no clue. It is not possible to predict. So totally it will depend upon how the nodes are actually filled up. Now naturally 30, 26, 25, just since I have taken an arbitrary value, that's why we can see that everything will be added in the right side. So a time will come where this particular side again filled, so someone will go and come join here, and again some time will come, this one will join. So one thing we have seen over here, that is point number 1, data is always inserted in the leaf node. Point number 2, uh, if number of key value uh, exceeds in a node, then one of the key value is considered as root, not root, you can say parent. One of the value is considered as parent of the node, and the previous node is divided into two part, right? So this is a way by which a root is evolved from the leaf node in what you can say bottom up approach. So these are the 3 points you should remember when you will create a B tree. So this is all about the creation of B tree, and there are many other factors also. When you will try to delete, then what will happen? And if I want to insert something, again I am saying that if I want to insert something in a B tree, for example, I want to insert say 4, then what will happen? 4 is lesser than 7, 4 will not join over here, rather 4 is lesser than 7, it will come here, 4 is greater than 3, so it will come here, and then 4 will join in this particular node. And if it happen that after joining, this number of key value in this node has increased the limit, has crossed the limit, then some key value, one of the key value will join with its parent node, and accordingly if it required to rejoin some node key value from here to its parent, it will go. So after inserting the node in the leaf node, maybe there will be joining here to here if required, if it is crosses the limit. So this is a way by which we can create a B tree, and you can say that this BST that we considered is of the one type of MOS search tree, but don't please mix up BST with B tree. The philosophy of creation of these two different type of tree is totally different. If you still have any doubt about the BST, you can go to my video and check it, but be very sure that they are not same. Anyway, so we can stop the class over here for the B tree creation. You will see in the next class how the B plus tree and another form of MOA search tree is created. Thank you.